We'll have a look at the conformational analysis of cyclohexanones and substituted cyclohexanones. The cyclohexanone will be having a carbonyl carbon on it, and the carbonyl carbon, we know that is sp2 hybridized, and therefore the bond angle must be 120 degree for this carbon. Now if it is in the planar form, this bond angle will be 120 degree. But we know that the cyclohexane does not exist in the planar form, it exists in the chair form in order to reduce the bond strain, since the rest of the carbon atoms of cyclohexane are sp3 hybridized, and the bond angle for sp3 hybridized carbon must be 109 degree 5 minutes. So cyclohexane exists in the chair conformation in the puckered form, and the cyclohexanones too exist in the chair form. Okay, now this is the chair form of cyclohexanone. Now this cyclohexanone, the carbonyl carbon, you can see the carbonyl oxygen is not exactly axial or equatorially oriented. Okay, now if we take the cyclohexane ring, as you can see here, the hydrogen atoms attached to the carbon atoms are either axially oriented or equatorially oriented. Now when we come to the cyclohexanones, the carbonyl oxygen is neither axial nor equatorial. It is placed in between the axial and equatorial orientation. Okay, and because of this sp2 hybridization of the carbonyl carbon, the carbon atoms attached adjacent to the carbonyl carbon and the carbonyl carbon all remain in the same plane. When we look at the three-dimensional model, it will be very clear. And one more thing, the equatorial hydrogen atoms adjacent to the carbonyl carbon are eclipsing the carbonyl bond. So you can see here C double bond O is eclipsed by CH bonds, the equatorial CH bonds. But when you take the cyclohexane, the CH bonds, all the adjacent CH bonds are the staggered form, isn't it? But here, the carbonyl carbon and the CH bond are eclipsing each other. And this carbonyl carbon experiences an angle strain because it has to exist in 120 degree, but then it is not in 120 degree, it is almost near to 109 degree 5 minutes. So cyclohexanones experience angle strain and eclipsing interaction. The eclipsing interaction is a dominant destabilizing factor. So these two destabilize the cyclohexanone when compared to cyclohexanes. So when you compare the stability of cyclohexane and cyclohexanone chair conformers, the chair form of cyclohexane is more stable than that of cyclohexanone, because in cyclohexanone there will be angle strain and eclipsing interaction. Now when you flip this, what happens? The carbonyl group goes to the alpha or phase, that's all. In the earlier case, it was in the beta phase, now it goes to the alpha phase. But here also the equatorial hydrogen will be eclipsing the C double bond O bond. And here what you have to keep in mind is the flipping of cyclohexanones from one chair form to another chair form is faster than the flipping of cyclohexanes. Okay, the chair forms of cyclohexane. Now why is that so? We will discuss in the next few minutes. Okay, so ring flipping in cyclohexanones is faster than that of cyclohexane. Now cyclohexanone belong to CS point group, so there will be a plane of symmetry, and hence cyclohexanones are achiral. Okay, cyclohexanone is achiral because there is a plane of symmetry. It belongs to CS point group. Let's now look at substituted cyclohexanones. As an example, we'll take up 2-methyl cyclohexanone. Now, when we write the chair form of 2-methyl cyclohexanone, we can write it in two ways. That is, the methyl group in the equatorial form or the equatorial orientation, or methyl group in the axial orientation. When we put methyl group in the equatorial orientation, the chair form or the molecule will experience eclipsing interaction and angle strain. Eclipsing interaction, as I said earlier, is a highly dominant or predominant destabilizing factor. Now, when we write the methyl group in the axial form, the eclipsing interaction is totally eliminated. Instead of that, the molecule will be experiencing 1,3-diaxial interaction. Now, so here there will be angle strain, 1,3-diaxial interaction, and additional butane gauge units will be introduced. Now, in equatorial form, additional butane gauge units will not be there. Alright, now when we look at the energy of these molecules, what we find is when we compare with the methyl cyclohexanone. In methyl cyclohexanone, there is no eclipsing interaction, there is no angle strain. Okay, when the molecule is in equatorial, when the methyl group is in the equatorial conformal or equatorial orientation, and there will be no additional gauge butane units. So in the equatorial form, the methyl cyclohexane will be equivalent to that of cyclohexane. But when the methyl group is in the axial orientation, then what happens? There will be additional 2 butane gauge units, and there will be 1,3-diaxial interaction. So energy wise, the equatorial form of methyl cyclohexane will be more stable, or will be having less energy. When you compare the equatorial forms of cyclohexane and methyl cyclohexanone, 2-methyl cyclohexanone will be having more energy because of the eclipsing interaction and angle strain. And when you compare the axial form also, it is the same thing because of the angle strain which is introduced. There will not be any eclipsing interaction. So the energy difference between axial form of methyl cyclohexane and axial form of 2-methyl cyclohexanone will be a bit less. Now, when we draw the energy diagram, we can see it more clearly. Now, if we take the case of methyl cyclohexanes, the equatorial form will be having energy same as that of cyclohexane. It will be at a lower energy state. But axial form will be at a higher energy state because of the additional butane gauge units introduced, and also because of the 1,3-diaxial interaction. Now, when you write the energy level of the cyclohexanones, 2-methyl cyclohexanone, the equatorial form will be having energy higher than that of the equatorial form of methyl cyclohexane because of the eclipsing interaction and the angle strain. Remember, the eclipsing interaction is a predominant factor. And that of the axial form of 2-methyl cyclohexanone, the energy gap between the axial form of methyl cyclohexane and 2-methyl cyclohexanone is less. You can see here, because the additional destabilizing factor is the angle strain. And also, the energy gap between the axial form of 2-methyl cyclohexanone and the equatorial form of 2-methyl cyclohexanone is less when compared to the energy gap between the axial and equatorial form of methyl cyclohexane. You can see the energy gap difference. Okay, because in 2-methyl cyclohexanone, when you compare the equatorial and the axial form, the eclipsing interaction is eliminated in axial form, but additional butane Gauge units in 1,3-diaxial interaction is introduced. The angle strain remains common for both. Alright, so the energy gap, if we put it as delta E cyclohexane, that is cyclohexane, short form I have introduced. Okay, so delta Cane will be greater than delta E Cone. Okay, because this energy gap is less, because the angle strain is less. The destabilizing factors are almost the same in both these cases, except for the eclipsing interaction. And so you can put delta E Ca is greater than delta E Cone. Okay, and because of this less energy gap between the axial and equatorial form of 2-methyl cyclohexanone, the axial form will be more in concentration. Substantial amount of axial form will be available in 2-methyl cyclohexanone when you compare with the axial form of methyl cyclohexane. Now, when we look at the methyl cyclohexane, they could 99.9%, almost 99.9%, you can say, exist in the equatorial form. Only 1 to 0.1% exist in the axial form. But in the case of cyclohexanones, 2-methyl cyclohexanone, the axial form will be, the amount of the percentage of axial form will be substantially high. Okay, and this is called 2-alkyl ketone effect. That is the considerable increase in the axial isomer of 2-methyl cyclohexanone when compared to methyl cyclohexane. Now, I have told you earlier that ring flipping is faster in cyclohexanones. Now, the reason is here. The energy difference between axial and equatorial form is large in cyclohexane when compared to the energy between the axial and equatorial form in cyclohexanones. And therefore, they flip faster. Okay, they interconvert at a faster rate. Alright, so this is about the substituted 2-methyl cyclohexanone. So 2-methyl cyclohexanone experience 2-alkyl ketone effect. What is 2-alkyl ketone effect? It is the considerable increase in the axial isomer of 2-methyl cyclohexanone. Even though we expect axial isomer to be in a lesser amount, there will be an increase in axial isomer, because in equatorial isomer there will be eclipsing interaction. Now, similar phenomenon is experienced in 3-methyl cyclohexanone also. Now, in 3-methyl cyclohexanone, what we find is when we write it in the equatorial form, there is no eclipsing interaction over here. You can see, because the methyl group is 1 carbon away from the carbonyl carbon. Okay, and there will be angle strain but no eclipsing interaction. Now, when we write the axial form, when this flips, the methyl group comes to the axial form, there will be 1,3-diaxial interaction. But here, this molecule will experience only 1,3-diaxial interaction. Usually for cyclohexanes, and in the earlier case for 2-methyl cyclohexanone, the methyl group will be experiencing 2 1,3-diaxial interaction. Here there will be only 1 1,3-diaxial interaction, because on the carbon to which carbonyl group is attached, there will not be any other group. Okay, so the axial form of 3-methyl cyclohexanone will experience only 1 1,3-diaxial interaction. So here there will be 1,3-diaxial interaction, additional butane Gauge unit, and angle strain. Alright, there will not be any eclipsing interaction. Now, when we write the when we compare this with the methyl cyclohexane, again, the equatorial form of methyl cyclohexane will be more stable than the equatorial form of 3-methyl cyclohexanone because of the angle strain. Okay, and the axial form will be more stable when compared to the axial form of 3-methyl cyclohexanone because of the angle strain. But and also the additional butane Gauge unit, but the this molecule will be experience only one 1,3-diaxial interaction, while axial form of methyl cyclohexane will experience 2 1,3-diaxial interaction. Okay, so you can say that the energy of these two axial forms will be almost the same, because in cyclohexanone there will be an angle strain, but in methyl cyclohexane axial form there will be an additional 1,3-diaxial interaction when compared to the cyclohexanone. So when we write the energy diagram, for methyl cyclohexanone, the equatorial will be more stable, and energy of axial form will be very high when compared to the equatorial form. In case of 3-methyl cyclohexanone, the energy of the equatorial form will be higher than that of the energy of the methyl cyclohexane equatorial form because of the angle strain. But the energy of the axial form of 3-methyl cyclohexanone will be almost same as that of energy of the axial form of methyl cyclohexane. And so the energy difference between the axial and equatorial form of methyl cyclohexane will be more than the energy difference of axial and equatorial form of 3-methyl cyclohexanone. So here also there will be considerable amount of the axial form, because since the energy difference between axial and equatorial is less, there will be more of flipping. Okay, so there will be considerable amount of axial form, and that is called 3-alkyl ketone effect. Okay, considerable increase in the axial isomer of 3-methyl cyclohexanone. So you have, for substituted cyclohexanone, there will be 2-alkyl ketone effect, 3-alkyl ketone effect. Now when we take another example, and that is 2-halocyclohexanone, instead of methyl group, we are introducing a halogen group. Now when you write the equatorial form of this, the chair form, what we find is, apart from the eclipsing interaction and angle strain, there will be dipole-dipole interaction. And when we write the axial form of this, when we put the halogen in the axial orientation, there will not be any dipole-dipole interaction, there will not be any eclipsing interaction, there will be angle strain and 1,3-diaxial interaction. Okay, so no eclipsing interaction and no dipole-dipole interaction in the axial form of the 2-halocyclohexanone. Alright, but in equatorial form, there will be angle strain, eclipsing interaction and dipole-dipole interaction. Because of this extra eclipsing interaction, which is predominant, along with that we have another highly destabilizing factor, the dipole-dipole interaction. The equatorial form is less stable, or we can say that the axial form is more stable. Okay, in the case of 2-halocyclohexanone, and that is called alpha-halo ketone effect. The considerable increase in the axial isomer of 2-halocyclohexanone, that's called alpha-halo ketone effect. Okay, so this is more stable. Now when we change the solvent polarity, in polar solvent, the concentration or the amount of equatorial form increases. That's because the polar groups, that is the halogen group and the oxygen group, will be solvated, and the dipole-dipole repulsion decreases. They will be solvated and they will be shielded from each other. okay, desolvation. So the repulsion decreases and slowly the amount of equatorial form increases. So you can say that the amount of equatorial form of 2-halocyclohexanone will be more in polar solvent, and that of the 2-halocyclohexanone axial form will be more in apolar solvent. Alright, now we'll take another example, and that is 2-bromo-4,4-dimethyl cyclohexanone. Okay, 2-bromo-4,4-dimethyl cyclohexanone. When we write the chair form, we can see that the bromine can be written either in the equatorial form or in the axial form. There will be 2 methyl groups attached to the carbon atom or 4th carbon atom, and even when we flip it, what happens? The methyl group changes the orientation, but it will be literally the same. Okay, because one goes to axial, the other goes to equatorial. Now, this is the equatorial form. There will be angle strain, eclipsing interaction, and dipole-dipole interaction. Now, when we write the axial form, there will not be any angles. There will be angle strain, but there will not be any eclipsing interaction and no dipole-dipole interaction. There will be angle strain and 1,3 diaxial interaction. Now, 1,3 diaxial interaction will be between the bromine and the methyl group. Here also, in equatorial form also, there will be 1,3 diaxial interaction between hydrogen and methyl group. But here it will be between bromine and methyl group, which will be higher. Okay. So, since bromine is a bulkier group than hydrogen. So, since there is no eclipsing interaction and dipole-dipole interaction, obviously the axial form will be in more concentration, or the axial form will exist more. Okay, so this is energy-wise, the axial form will be, when you compare with the equatorial and axial, see, because equatorial is experiencing eclipsing interaction and dipole-dipole interaction, but axial form is not experiencing any eclipsing interaction and dipole-dipole interaction. So axial form will be more stable. Okay, so these are a few examples which we have taken for substituted cyclohexanone. So keeping all these points in mind, you can try to explain the conformational analysis of any substituted cyclohexanones. Okay, and remember here the equatorial form will be more stable in polar solvent, while axial form will be more stable in apolar solvent because of the solvation. Okay, so keep in mind in eclipsing interaction, dipole-dipole interaction, angle strain, 1,3 diaxial interaction, butane Gauch units. Okay, and then explain the conformational analysis of any cyclohexanones which is given to you. Okay, please write the structures and make yourself thorough. Practice writing the structures and make yourself thorough about the concept. Thank you.